I'll try to explain briefly. Myself, I'm a PhD student in planetary geology at Giacomo University in Bremen, and I'm focusing on planetary mapping using machine and deep learning techniques. So here I'll try really briefly to explain my approach to planetary mapping as a beginner on of both programming and artificial intelligence, using as a sense case the sinkhole-like landforms detection. So, but what is planetary mapping? Planetary mapping is just a comprehensive representation of the features that characterize a planetary surface. Features that may include both material properties like temperature, chemical composition, or morphological properties like color, texture, shape, and so on. But map creation usually includes several tasks that usually needs to be performed by researcher manually. Data that includes data analysis from data selection, data analysis, symbology definition, and really more others. And this is a really intensive and long task since it's all done by hand, by researcher. In some cases, there are some semi-automated workflow that help researcher to map or at least filter the data, so it could be easier to do the proper mapping. But in planetary mapping of other terrestrial planets like Mars, Moon, Mercury, and so on, is not so simple, and there aren't specific mapping tools. Moreover, high detail maps are usually specific to small areas of a planet, while low detail maps are available even at a planetary scale due to the high amount of work needed to map to produce a map. But the enormous difference for mapping between the mapping done on Earth is that on Earth, researchers and mappers could go on the field and collect data directly, while on extraterrestrial planets like Mars, we don't have the possibility to go there, at least now, and collect data and evaluate with our eyes and maybe take sample and so on. Yes, we have some rovers that are collecting data in situ, but is not the same since rovers are located in very specific environments, yet they are really useful. So in planetary mapping, the major difficulties are the starting from the ground truth data. Since mappers can go there, it's quite impossible to get ground truth data, apart of the location where there are rovers that may collect data. But also there are the dataset size. For example, for Mars, over the past decades, over 40 petabytes of data has been collected from orbital, and that data include hyperspectral data, optical images, radar, and so on. So it's really a huge amount to be performed at a planetary scale, mapping in a planetary scale. So in fact, usually mapping are done in a very specific region of interest, for example, the Jezero crater where the Perseverance has landed months ago, or really spot areas. So in this case, I thought that machine learning and deep learning could play a key role exploiting the analysis of the planetary surfaces. So really briefly, deep learning for image analysis could be summarized really roughly into 4 major classes that are the image classification, the image segmentation, object detection, and further the instance segmentation. And with a complex level that go through and rise going to instance segmentation. But in this situation, there are several works that I have the planetary mapping as a main topic using deep learning, but there are no, at least now, or at least in not publicly available, tools and specific workflow that are available for everyone, just like ready to use or almost ready to use for researchers that are interested in mapping specific landform, for example, in a specific area. They need to do all by scratch from zero if they want to use machine learning or deep learning approaches. There are some proprietary softwares, but are specific for Earth observation and yet not suitable almost never to data collected by extraterrestrial satellites like on Mars or even the Moon. Some of them are specifically modified and adapted to read this data, but doesn't support the mapping or the automatic mapping. So if each researcher that want to map with machine learning or deep learning need to go from zero to a final product that they can use, it's a really huge task, and it's a huge effort in both in time and resources that need to be spent by researchers. So in addition to that, considering that there is a wide availability of frameworks, architecture, and programming languages that could generate more confusion than rather than clarification, especially for a beginner person. For example, I've started from zero for artificial intelligence and some of Python programming languages. It's really a nightmare to start to produce something and create something from zero. So my approach was kind of different. I just tried to focus not on the techniques at the back or at the core of deep learning and machine learning techniques, but rather than to the front end, so the tools that and workflow and architectures are already done by others, but can be used and adapted for mapping. So I started with Python just because I was already familiar with it, even if it's a basic level. Then I moved to other frameworks and look for frameworks and pipelines and tools already published and publicly available as an open source, even if not in the planetary sciences, so like even for autonomous driving or face detection and whatever, and try to look for potential adaptation and integration in a planetary mapping context. So I decided to go gradually from object detection to instant segmentation, because it's there is a lot of complication moving from just object detection to proper segmentation. So the objective was and still is to create a set of very easy to use tools to train and perform and use models specific for user-defined landforms. So for example, I'm focusing on caves, but others researchers in planetary science may be focused on, I don't know, craters or volcan specific expression. So I tried to create something that was more general and general as possible, yet still focusing on a specific landform that, as a test, that are the cave candidates. To do that, I've decided to go with YOLO, that is you only look once, version 5, published by Ultralytics, that is an object detection architecture of deep learning, open source, publicly released on GitHub, and well documented, well maintained, still yet maintained, and based on PyTorch, Python, and it's almost ready to use. It's ready to use if you want to classify or detect common objects on Earth, like the usual example of dog versus cat versus car versus person, for example. But yet it was still adaptable to use georeferenced images. So images took from orbit or airborne. To do that, I've produced two Jupyter notebooks, one for training and one for inference, based on this package, slightly modified, and tested with sinkhole-like landforms. Also, I've created a whole workflow for the whole process, just to visualize better all the steps that I needed to be all the steps that needed to be done to achieve these objectives. So moving to the specific case of the sinkhole-like landforms, just a short introduction on these landforms. Sinkhole refers to different morphologies that have in common the processes of depleting materials into an area within the morphology itself. It's like a pothole, or yeah, on Earth, like the cenotes in Mexico or in South America. These are the major expression of the on Earth, at least in the karst environment, because these landforms could occur both on volcanic and karst environment, at least on Earth. Another planet is still debated because we don't know if there are large karst environments and deposits that could generate such landforms, while it's more sure that this landform, for example, on Mars, originates in volcanic sediments like lava floor or lava tubes and so on. The mechanism at the base of the formation of these landforms here on Earth are essentially related to the depletion of sediments in the subsurface or the collapse of underground cavities, while, as said, on other planets is still debated, but it's more focused on volcanic processes, related to volcanic processes. Regarding the data that I've used high resolution images up to 30 centimeters per pixel, produced by HiRISE instrument on board on Mars, a reconnaissance orbiter around orbiting Mars, and CTX on board of the same satellite, the Mars Reconnaissance Orbiter. In order to accomplish the objective of create a consistent environment, both for train and infer the images that users could ingest to both of these notebooks, newer tools needed to be created for processing the original images, because are not simple images, are usually provided by space agencies in form of raw data. So are not yet processed for direct use, like JPEG or PNG format, or even TIFF. So I needed to create some new tool to consistently create images that can be then ingested for training and for inferencing. So after knowing all that, so defining the landform to be used, defining the workflow, and defining the tools to be used, I was able then to start with the most tedious task, so the data selection and labeling. For starting, I've selected 130 more or less HiRISE images over the Tarsis region on Mars. I've selected this region because it was already investigated by Cushing et al. For creating the first database of Mars cave entrance candidates. That is a database that includes the location of over than 1,000 possible pits or similar landforms, but is all created manually using both HiRISE and CTX images. But this database does not include directly information about the images that caching I use. So I needed to select manually more other images. So the images that I've used are not exactly the same that caching I used. And this is a double phase thing, because it could be helpful since more images could be elaborated, and but could be not precise enough for a direct comparison with the database, because the images at the base of the analysis are not exactly the same. So these images, since these images could reach up to 1.5 gigabyte each, and a dimension really above 80,000 of pixels per side, I needed to create another tool to tile them, maintaining the georeferential information, because it's vital for mapping, know exactly the location, not only in image coordinates, but also in geographical coordinates, so planetary coordinates, to be then converted back into a proper mapping products. So I created another tools to produce all of the styles and also filter the not useful ones and slightly reduce the work to be done into these images for labeling. So after that, I created all the 5 classes that basing on literature, essentially, both of caching and others, that are that range from type 1 to type 5, that is the creator. That all of these lens forms and classes are really similar, because both all of them have a circular shape, are shallow, or could be dark and covered by dust or other sediments, but and especially the rim is sharp, while in others, like for example craters, the rim is not sharp but present a bulge. So I decided to include this to try to see how such architectures perform, describing really similar images, but yet different from an objective and a researcher point of view. So after that, I've done the proper training with a pretty good result, because even if with a really small data set, I was able to achieve a 75% of mean average precision, a precision of 80%, and a total recall of 70%. So it was not excellent, but nor bad. So it was pretty good as a first starting point. And so moving on the results obtained on the images that are more explainable and more visible to a mapper or a geologist, we can see that on HiRISE there is a really high detection and precision on detecting this landform that has been trained. With class 5 that are the craters, and class 1 that are the best candidates. But not only on HiRISE, also here is still HiRISE, but also in CTX, even if the resolution of CTX is up to 6 meters per pixel. So it's not the same, because for the training of deep learning model for object detection, resolution of the regional images, so the resolution of the labels, are a key point. So if I train a model on really high resolution and then try to test it on really low image resolution, results could be really bad, because the resolution are not the same. So, but yet there are still really good as a result, as a preliminary result. But the most interesting things and results are represented by, before that, I've tried to compare the results that I've obtained with the database of caching that are here represented in red stars. And as we can see on the images, there is a really high correspondence of the detections, especially if we go in a higher detail. We can see, for example, in this image that the detection of the deep learning are exactly corresponding in some images where the images are the same with the ones present in the database of caching. While the plot in the hole in the center is due to the fact that I hadn't used the same image that instead was used by caching. Lastly, the very interesting result obtained is that not having used the same images that caching has used, we and I was able to detect new images, new landforms that are not present in the caching's database. And even if there's still the needs to be manual validated by experts, it's still a good result because for a light view, or even if it's not from expert point of view, we clearly almost be sure that this new detection are easily and for sure be included into a new database that may be released in the future, expanding this model with more training data and inferring hopefully at a planetary scale. And lastly, further works that are still in development are the instant segmentation, and preliminary results, really extremely preliminary results, are really good because, as we can see, there is a really good detection and instant segmentation of the landforms trained with the same images as the object detection model, but for instant segmentation. And in such case, we can move directly from newer images, unseen images, up to geopackages or shapefile that are the common file types used by mappers to produce maps and evaluate other parameters. For example, if we interrogate these shapes produced in a GIS software using, for example, a base map like an elevation model, we can extract not only the dimension, like the area of such a landform, but also the 3D volumetrics of this landform, so the height and the overall volume, and further improve the knowledge of this landform. So that's it. Thank you for your attention. And if you have any question, I'm here.